Let's start the morning session of the second day. So our first speaker is Yu-Dai Tsai from California. So I guess he'll be talking about some new ideas on probing fundamental physics. Please.
Yep, I heard some reflection, but I should be fine. Okay, thanks for the introduction. So before we start, let me share something. Because I know it's very early. Let me share a video very quickly. Wake everybody up. So this video that I show is an asteroid event that hits Russia, and we will talk about it later. But I will wait a little bit to talk about it. First, I will introduce you to things that is happening right now, the new technology. So let's get into it. And you using this technology and data to study ultralight dark matter or ultralight particles. So the big questions that we want to ask is, how much dark matter are there in the solar system right near Earth? Not the galactic dark matter, but in the solar system. Do we really know how much? And secondly, can planetary data set a meaningful model independent dark matter constraints? How about general relativity? How about fifth forces? So that's the second question. The third question is, can we use the current or future space quantum technologies to study fundamental physics? So these are all interesting questions. And the answer is, first, we don't really know. And I will explain to you why. And also, yes, we can use planetary data to set meaningful dark matter constraints, and including dark matter, general relativity, and fifth forces, yes. And thirdly, and this is the first question we will start talking about, is that there's future space quantum technology and current one, and we can use them to study fundamental physics. Okay, so today we'll bridge all these new kind of emerging direction and planetary science, space quantum technology, and fundamental physics. And there are actual real life consequences. So the first thing you know is this spaceship, Starship, that is actually in the UCI campus. So it's moving around to deliver food, and maybe in the future it will deliver other things, who knows? Maybe it will carry students around. But anyway, this is the self-driving Starship. So the fact that I'm mentioning self-driving Starship is directly related to the recent development of the NASA Deep Space Atomic Clock. So we're developing a lot of, in NASA, we're developing a lot of very precise atomic clock that lose 1 second every 10 million years, meaning that there is a fractional frequency stability of 3 times 10 to the minus 15, meaning that you only lose 3 times 10 to the minus 15 seconds after 1 second. So it's very, very stable, very, very precise. That's the first thing. Secondly, there's the Parker Solar Probe that is going near the sun to study solar corona. It's happening right now. So I would say the Parker Solar Probe, just like JWST, the James Webb Space Telescope, this is another big scientific event, but this is happening now. So it's already taking data right now near the sun. So the idea, very simple, is what can we do if we put deep space atomic clock on the Parker Solar Probe for the future? Okay, that's the question we can ask. So you ask me, how does this relate to spaceship? Okay, so if you want to do space traveling in the future, even now, if you want to land on the Mars, you land on the moon, you need to time things very carefully, because if you miss a few seconds, it will miss a long distance. But more than that, if you want a self-driving spacecraft, you need to time the distance very precisely. You need to have a GPS system. So you need to actually have atomic clocks in the many places of the space to time things very carefully. So you want to have a deep space and global navigation system, which is called GNSS. It's basically the space version, the expanded version of the GPS. And NASA is developing that right now. And we can use all this technology to study fundamental physics. So one day, if we need to escape the Earth, we can go to sleep and auto-driving spaceship will take us to a new destination. Of course, this is in the far future, but NASA is already developing these technologies. Now, just get back to the more realistic thing, that is the atomic clock. So first you ask me, why is atomic clock so important in the space? One thing that can be overlooked is how we actually get the distance, right? How do we actually locate things? We actually locate things with atomic clock, because the way you determine distance is you send a signal to something and it comes back, whether it's radar or it's light. And that is how you get the distance. So you need to time it very well. So you need to use atomic clock to time things very well to get the distance. So time is not just about time. Time is also about distance. Okay, so what is the best timing? Of course, now is the atomic clock. One of the standard is the CCM standard. That is how we define second now. So we use a very, very precisely measured this energy level to define this as something hertz. So how many cycles a second? Use this to define the second. So this is currently how the second is defined. Okay, so let's get into fundamental physics. Here's an outline. First, I will introduce ultralight dark matter. I will talk about the solar bound state halo and the sensitivity of a space-based clock. So ultralight dark matter. So we all know ultralight dark matter pretty well by now. I will not get into all the introduction. Other people will talk about them a lot. But the idea is that you can have this dark matter, ultralight dark matter, coupled to electron, photon, and gluon. Now, there are some of these mass parameters, forget about them. What's really important is the coupling is to phi EE, phi FF, and phi GG. G is of course, the gluon, the QCD coupling. So this is the atomic clock. People like to use this kind of notation, but ME is not really that important. ME is just a parameter. You don't even need ME here. So it's just really a coupling. Now, once you have this coupling, you can solve for the dark matter equation in the non-relativistic setting, because these are wave-like dark matter and they are non-relativistic. You find out that they will oscillate and the frequency is about the same as the mass. So these are wave-like dark matter and they also oscillate like a wave. So because they oscillate, they will affect the fundamental constant because they're coupling to electron, photon, and gluon. So these will actually introduce the fluctuation in the electron-proton mass ratio, the alpha, which is the fine structure constant, and the strong coupling constant. So all of these three will be affected. Now, once these are affected, because you introduce this fluctuation, you can measure them with atomic clock. So how do you do that? So there are some detail from this paper, but the basic idea is these frequencies are directly proportional to alpha, which is the fine structure constant, times index. So in principle, it's more complicated, but I turn off D and D, ME and DG for now, just for simplification. So I only turn on D alpha. Now, alpha is related to these effects from the dark matter. So eventually, if you have two different clocks, you have two different frequency, then you can measure the difference in the frequency. And then divide it, there's a normalization, which is determined by this CA and CB, which are well known for the frequency. Then you can extract the D alpha. So D alpha can be extracted. So this is the experimental observation. On the left-hand side, here is known already from the calculation. So you can determine the D alpha. So that's how you do it. And some examples are hyperfine microwave transition or electronic optical transition. These are the clock transition. So in principle, you don't need a clock, you just need a transition, but we already designed a clock, so might as well directly use the clock. Okay, good. So this is how you get the dark matter constraint. Now the interesting new things comes in to consider the solar bound states. So the solar bound state has been considered by many different people. One of the recent group is this group, and then they consider if you have external field, what kind of bound states are allowed in the solar system. So now you ask me, Why is the solar system dark matter not the same, just like the galactic average? It should not be, because there's a complicated history of solar system evolution. The gravitational potential have changed drastically. So there is something called adiabatic contraction that can concentrate all this dark matter near the solar system. So it's actually not generic that there is no extra dark matter nearby. There should be extra dark matter nearby. The question is how much? So here is a solution that is consistent with this. If you have this potential, you can solve for it, and then you can have this kind of bound state structure. And the bound state is exponentially dropped. This radius is determined by the mass, and this m rho is an overall factor that we cannot determine directly from the principal calculation. But we have model independent constraint on these based on planetary data. So here is when the planetary data comes in. Because we measure these planets very well, like Mercury, Venus, Earth, Mars, Jupiter, Saturn, and also asteroid, which I'll talk about more. So you actually have all this data to set the constraint. So your dark matter bound state have to be smaller. You cannot exceed these. And these are the density constraint. So you can see that here we're plotting, in our paper, we're plotting the bound state within these densities. And you find out that if you have a little bit higher mass, then you can have more bound states, like the brown one. If you have a more lighter dark matter, then you cannot have too much. Okay. So now the question is, if you go close to the center, go close to the sun, how much more dark matter can you see? So here we plot three locations. One is on Earth, is 1 AU. The red one is on the Mercury, and the blue one is on the Parker Solar Probe, and it's 0.1 AU. So you find out that for a range of mass, it doesn't matter. You see the same amount of, you see basically the same amount of bound state dark matter. But if you go to these around these 10 to the minus 13 mass, if you can go close to the sun, you can have a drastic enhancement of the density. So your chance of finding this dark matter will be way higher. So this is the interesting thing. So that's why we want to put atomic clock, 2 atomic clock on the Parker Solar Probe kind of thing in the future to search for these bound state dark matter. And a side note is that now, since we know about this, I'm working on with many people to update all these constraints. And this is ongoing work, so I will not talk too much. But the idea is to also add the asteroid data, which I will say a few words about later. Okay, so here is kind of the conclusion. So with this kind of enhancement, the clock that are close to the PSP or Mercury, you can actually probe this region way better because you have the bound state enhancement. And it allows you to probe deep for the naturalness line and the HP relaxion line. HP is the Higgs mixing. And so this is for the electron coupling. This is for the alpha, for the fine structure constant, coupling to the fine structure. Coupling to not the fine structure, the coupling to the photon coupling. Now, what is this naturalness curve? You ask me. So naturalness curve is, for example, your phi is coupled to electron. So you have an electron loop, and then you need to keep it. You need to keep it natural. That's the curve of prediction. HP relaxion is when you have a scalar maximally mixed with the Higgs. This is the prediction of the. You need to be smaller than this value to be natural. So you have all these different kind of prediction, and you can see our paper for a detailed discussion of these curves. And it's also been discussed in the previous paper by Gillas group. Okay. So here are the dark matter results. But how about more on the planetary constraint? So here I show you the dark matter. How about the generic ultralight dark sector or fifth force? Independent of the solar bound state, let's forget about solar bound state. Let's also ask about other ultralight dark matter sector. So as I show you in the beginning, we need to be very carefully monitoring all these different objects. And recently there's a movie called Don't Look Up. And in reality, please, we should look up. And there's a global effort. I think Japan is involved. I think Korea is probably also involved. All the telescopes are pointing to the skies to monitor these. The European Space Agency is involved. NASA is involved to monitor all these minor objects in the sky because they can kill us. That's how dinosaurs died, and they will agree that we. And actually, in 2013, this is the event I showed you. More than 1,500 people are injured seriously enough to seek medical attention. So this one was unexpected. So we need to reduce the chance of unexpected events. And there's so many, so we need to really track all of them pretty well. Now, because we track them very well, we can use them to study fundamental physics, just like James Moriarty, which is from the Sherlock Holmes novel. He's also spent a lot of time studying asteroids. So there's all the different kind of asteroids you can study. And because of that, you can use this data to study fundamental physics, including the dark matter constraint, but more than that. So the model-independent dark matter constraint, for sure, I mentioned, but there you can also study other things. And one quick note is that you can do radar observation because you can send a radio signal to the object and come back. So you can get the distance, line of sight distance and line of sight velocity very well, which is way more precise than all the other kinds of astrophysical or cosmological measurements. Okay. So the most basic thing that we will think about, just like 100 years ago, people are already doing that, is the general relativity. So general relativity will induce the precession of the asteroids and also other planets. So if you study the precession very well, then you can constrain general relativity. So this has been done for the planets and also recently been done for asteroids. So this is for the precession of for general relativity. So now, so this is the term for the general relativity. I will not get into detail. And we fix things on the planetary motion. And here I introduce A. A is the semi-major axis defined like this. So it's the longer axis here. Now, if you have long-range force, like Yukawa type coupling, so you can have this kind of Yukawa type coupling, exponentially decay with so these are the same equation. One is just the particle physics side, one is the generic parameterization. But either way, you can have both attractive and repulsive force. Once you introduce this coupling, you will induce a new term that will induce the precession. So the precession will be induced if you have a Yukawa type coupling. Now, this Yukawa type coupling can be induced from a scalar or vector. And scalar, you can just have whatever coupling you want. For the vector, you can have this kind of U1b or U1b minus LE minus L mu tau. So all these you can constrain. So this is when you induce this, when you have this long range force, you can have this kind of constraint that is proportional to A actually. So it's proportional to the semi-major axis. For the GR is inversely proportional to A. So this means that you actually want to study asteroids further away from the sun. So if you can study asteroids further away from the sun, the precession will be actually stronger for the fifth force and will be weaker for the GR. So that's why in the past, people only study near Earth asteroids, but now you should study asteroids further away from the sun. Okay, so that's what we do. So we reuse one of the papers, study general relativity by this UCLA group, and we repurpose it to become a probe for the ultralight dark matter. We require the ultralight dark matter contribution to be smaller than uncertainty from the beta parameter in the general relativity, and this J2 is the solar abruptness and their correlated error. So this is just an estimation. We're doing a detailed analysis by actually modeling all the trajectory, but a quick estimation will give us these kind of the potential bounds. And this bound is actually very strong compared to the equivalence principle test if your long range force is roughly constraining, preserving equivalence principle, because equivalence principle test is testing if the equivalence principle is conserved, right? So if your long range force is preserving equivalence principle, it doesn't test it that well. But of course, you cannot really preserve equivalence principle completely. So if your equivalence principle is preserved in the percentage level, then the asteroids and planets are way better than the EP test here. So this is our kind of the results. So asteroids and planets are very strong in probing equivalence principle conserving long range force. And equivalence principle, of course, is you can drop two different mass and see if they land on the Earth at the same time. It's basic like this. However, if you are breaking the equivalence principle, then equivalence principle test, of course, is much stronger. So then the asteroids does not do so well, but it does not do much better, but it's still better in some regime. So, and we also plot the optimal bound that is in the 2022. So they did the analysis. The UCLA group did the analysis back in 2017. And there's a projection for 2022. So we also plot the projection for 2022. Okay. In summary, there are all the different kind of asteroids that you can study, not just the near Earth one. So the UCLA group only did 9 of the near Earth one, but there's way more. So in principle, you can study all these different asteroids with different semi-major axes. So you can have a spread of different kind of probe for the long range force and also for dark matter. So for the long range force here, I plot a kind of a projection of different kinds of different probe further and further away from the sun. So near Earth object is smaller than 1.3 AU for the perihelia, but for the main belt, it's a little bit further away. Hilda is a little bit far away. Jupiter Trojan is the asteroid that go with the Jupiter, and there are trans-Neptunian objects further away, and extreme TNO much further away. So you have a large spread in the semi-major axis, which means you can probe different parameter space for the dark matter in terms of the mass, and also different kind of in terms of the radius, and also different kind of long range force depending on the mass. So here, that's how we plot the different kind of probe. Okay, good. So for the future, we're actually collaborating with Q-Sense collaboration, which is a quantum sensor kind of, we are having a lot of discussion of how we can have the next generation quantum sensor in the space to study fundamental physics. And here are a few ideas. We can do the asteroidal planetary tracking array to track all these asteroids and planets and set constraints. We want to set the model independent dark matter constraint. Also, we want to improve the lunar ranging or lunar laser ranging. We want to have a next generation kind of lunar laser ranging or radar ranging to know the distance between the Earth and the Moon very, very precisely, and the trajectory. And you can also use that to constrain relativity and dark matter and all kinds of different things. So it's a very exciting time to do all this kind of thing, especially combined with the quantum sensor. And that's it. Yeah, thank you. And thank you very much, and happy to discuss more. And I will add a reference. There are some reference still missing. I'll add a reference in the end slides. Thank you.
Thank you for very interesting talk.
Thanks a lot.
Okay, so any questions and comments?
I have one question.
Okay, go ahead.
How much order do we need about the precision of time? I meant about 10 to minus 3 seconds or 10 to minus 4 or more?
You're asking about, okay, so yeah, maybe I didn't say it too quickly. So let me just show you here. So, okay, so this is the precision of the clock. This is corresponding to 10 to the minus 14, 10 to the minus 18. So 10 to the minus 14 is the best is almost the best of the space clock. Actually, space clocks are a little bit even better. It's 10 to the minus 15, but we choose 14 to be more conservative. So this is saying that your clock will slow down 10 to the minus 14 seconds every second. So every second you will lose 10 to the minus 14 seconds, and that's extremely precise. But on the Earth, you can do 10 to the minus not 18, so it's extremely precise. You almost don't lose any seconds for 1 second. So this is the best sensitivity on Earth. For the nuclear clock, you also can do 10 to the minus 18, but there's an enhancement factor that I don't have time to talk about, allows you to probe beta alpha. But maybe, I don't know if this answers your question, but I also want to just mention this. Oh, and there's also already existing bound set by atomic clock. But is this what you're asking about?
Well, I meant how to say, for fortschrittlich traveling space.
Oh, that's a
Yeah.
great question. So in the space traveling, the more precise, the better, that's for sure. But we can see how much distance you will run by, right? So because we're usually measured by the speed of light, so you can just times the speed of light to the losing second to determine how much distance you're off. For example, if you're landing on the moon, then you can calculate what's the precision you need. If you're going to outer space, you can calculate how much precision you need. I don't have that specific in mind, but for different mission, you need different precision. And that's why you want the clock to be as precise as possible. But the way to do it is basically just time this difference of the time to the speed of light to see how much you will miss the distance. Yeah.
Mhm.
Yeah. But
Thank you.
Thanks for the great question. Yeah.
So here,
Mhm.
can you stay on this slide? Okay, so here I am confused about the dimension of DME.
Yeah, that's so okay. DME is we made it dimensionless by having this insertion of this mass here, but the mass is not well, actually
No, phi is the scalar field has dimension 1, right?
right, actually, yeah, I
Then-
think there's a mass dimension. Yeah,
So, it appears that DME is 1 over mass.
right. Yeah, I think we normalize it. Sorry, I think I'm showing the old
Yeah, what kind of normalization you?
yeah, that's this notation need to be checked.
What is a kappa?
This basically DME is just the phi EE coupling. The mass doesn't matter, but because we're matching it to the atomic physics notation, that's why we put it
Okay.
here. But it doesn't matter. Yeah, I'll update the slides.
And so probably what you plot is just the dimensionless parameter, right?
Yeah. There's a
Okay.
so I should just
Probably
have
the single coupling probably.
yeah, I should just normalize it with the right mass. Yeah.
Okay.
We're when we do it, we always use the just dimensionless, but because somehow atomic clock people, they like to put an ME in. So yeah, sometimes we're confusing ourselves, but yeah, it's just some dimensionless thing. So
You
Okay.
have a kappa. You have a kappa there, right?
oh yeah. There's a kappa. Oh, sorry, yeah, I forgot the kappa. Yeah, kappa is absorbing it. Yeah, sorry, I completely forgot. Yeah, kappa is defined. I should put okay. I will add a kappa definition here. Yeah, kappa is absorbing the mass dimension. Sorry, I forgot. Sorry,
I have one question about the planetary motion in the presence of this new extra potential. Could you show this equation of motion?
sorry. Oh, okay. Yeah, good. Sorry, I was.
Yeah, probably next slide. Yeah, this one. So,
Mhm.
no, the previous one. No, this slide. So the equation in the box.
Mhm.
So how could you explain a little bit how you derive this term?
Yeah. So basically you have to you have to add this potential into the general equation that governs this U, and there's a long derivation. And once you, sorry, let me think what's the most concise way to do it. Yeah, basically you just have to add this potential into your Lagrangian, your Lagrangian, and just derive this equation of motion. It's basically the same way, but you need to, it's a long derivation, but
Okay, thank you.
yeah. Oh, but yeah, so sorry for all the mass dimension. Yeah, let me just clarify. So for all the mass dimension is absorbed in this kappa term, and this kappa term is defined in our paper. I should add it here. So
Oh yeah.
Yep. Thanks.
Okay, good. Time is up. So thank you.
Thank you.
So we move to the second talk by Nicolas Bernal.
Yes. Can you guys hear me?
Yes.
Okay, let me share.
Yeah, we see your screen.
Okay. Okay, so thank you very much for the invitation. It's a pity that it's online. Hope next time will be there, right? In person.
Sure.
Okay, thanks. So we talk about dark matter and primordial black hole. And it's based in this series of works made in collaboration with Oscar Zapata, Joel Perez, Fatola Karim, and Yongshu. I'm from Nicolas Bernal from Universidad de Narino in Bogotá, Colombia. And it is very late, 8 p.m. Okay, I don't think I have to convince you guys about the existence of dark matter, just to say that, I mean, there's this missing gravitational force, right? But just to emphasize that all probes that we have so far are this missing gravitational force, right? So that's what we have for now. And we don't know what dark matter is. However, we really like dark matter to be a WIMP, just because in that case it will be kind of, at least in principle, easy if you want to probe it. I mean, to produce the collider, to have direct detection. And the idea with WIMP is that dark matter reach a chemical equilibrium with the standard model, so that we can have both annihilation and production of dark matter in the early universe, and that these reactions happen at the same rate. That's what chemical equilibrium means. And typically for WIMPs, we need couplings of the order of 1, say 10 to the minus 1, 10 to the minus 2 or so. However, that's not guaranteed by any means. I mean, couplings between the two sectors could be much smaller. For instance, in the case of thin dark matter, where the basic idea is that, I mean, we have like the same Boltzmann equation, the same dark matter that is produced in the early universe. However, what we want to avoid is a chemical equilibrium. So in the early universe, the idea and the thin mechanism is that dark matter is produced, but the back reaction, so the annihilation is not there. And if it's there, anyway, these reactions are not in chemical equilibrium, right? So that's the idea for, at least for the infrared thin paradigm. And it could be realized having small couplings, and I say small, very small, say typically 10 to the minus 10, 10 to the minus 11 portal couplings between the two sectors, to be compared again with the WIMP, which are couplings order 1 or so. However, these small couplings, the very small couplings, it's not even guaranteed, right? So we can very easily think of scenarios where there's no Higgs portal or neutrino portal or kinetic mixing between the two sectors, and it's like a nightmare scenario where the only portal between dark matter and the standard model is gravity. So what if dark matter only couples to the standard model via gravitational interaction? And that's the only thing that is guaranteed, right? So we cannot avoid that. We cannot tune. There are not free parameters to tune, because the coupling is the Planck mass, which is a bit fixed, right? So what happens in these kind of nightmare scenarios, at least for us particle physicists? So, well, it doesn't have to be that sad. not that bad after all, because there are ways for producing it. And one way, for instance, is Hawking operation. If you have primordial black holes producing the early universe, dark matter will be unavoidable produced via Hawking operation of such guys. So what are primordial black holes in nutshell, just a slide? So the idea that with the very early universe can have large energy fluctuations that can collapse into black holes, into primordial black holes in the very early universe. So once they are produced, they will lose mass by emitting all particles via Hawking operation. And if you want at the very first approximation, the PBH will have a black body spectrum with a temperature which is the inverse of the mass of the black hole. So once produced, they will start losing mass. So the mass will decrease. That means that their temperature will increase, right? So they will be able to produce particles lighter than their temperature. But as the temperature is increasing because they're evaporating, at some point they will radiate all particles that exist. So at some point, in particular, PBH will radiate dark matter, no matter how heavy these particles are. Another point is that these black holes are light enough, and when I say light, for me, it's lighter than, say, a few or hundreds of tons. They will completely evaporate before the onset of BBM, and therefore they will be very poorly constrained. We'll see. Of course, if you want to be very picky, this mechanism for production of primordial black hole is super complicated because you have to take how the density fluctuations evolve. I mean, a model for inflation, for reheating. However, here we'll take an effective approach where all primordial black holes will be encoded in 2 free parameters. For instance, you have a single one, it will characterize by its mass at formation. Or if you want the mass at formation, which I'm calling M initial, can be traced with the temperature of standard model BAT at formation, right? We're assuming that they have no charge, and the effect of spin is very mild. I will comment on that at the end. So for instance, we're assuming Schwarzschild black holes. At the end, I have a comment about Kerr black holes. So that's for a single one, or where we don't want a single one in the universe, we want a collection, a number of the primordial black holes, and that's encoded in this parameter beta. And beta is exactly defined as the ratio of energy densities. So black hole energy density normalized by the standard model energy density at formation. So at T equal T initial. Okay. So now what about the dark matter from primordial black hole? So the idea of dark matter density is basically the primordial black hole density times the number of dark matter particles emitted per primordial black hole. And it's possible, I mean, as black holes if you want the first approximation, have a black body spectrum, it's possible to analytically compute the dark matter number density emitted by Hawking radiation, and it only depends on the dark matter mass and primordial black hole mass, right? So if for light dark matter, we have this first expression, where it's basically the ratio of the initial mass over the Planck mass square. And for heavy dark matter, heavier than the initial temperature of the black hole, is Planck mass over the dark matter mass square. Another important thing is that as primordial black holes scale like non-relativistic matter, its energy density goes like 1 over the scale factor cube. They can eventually dominate the total energy density of the universe, and therefore give rise to a non-standard expansion era of the universe. So we'll see that in the next slide. For instance, here. So here I'm showing you a plot of basically the parameter space for characterizing PBH. Here I have the mass, the initial mass of the PBH in grams. So we're interested in kind of light black holes. So in the range of grams to tons, yeah. And that corresponds to initial temperatures of, I mean, the temperature, the standard model temperature at the moment of formation between 10 to the 16 to 10 to the 12 GeVs or so. We don't want them to be much lighter because that corresponds to very high temperatures, which is in conflict with the inflation scale. So Planck data, basically. Also, I don't want them to be very, very heavy because they're very heavy, they will evaporate very late, and therefore the entropy injection could give problems to BBN. So they want them to completely evaporate before the onset of BBN. And here is beta, is basically the amount of dark matter, of primordial black hole, sorry. So I want to avoid very, as I told you, very light black holes, very heavy as well for BBN. And this part of the parameter space here is in conflict with, I mean, I'm generating too much gravitational waves that also could make troubles with BBN. So I want to be in this white parameter space here. If very large values of beta will correspond to a PBH domination at some point. However, if I have a beta small enough, I will always have a universe dominated by standard model radiation. Here I'm showing you the parameter space of these 4 lines that give rise to the whole dark matter, observed dark matter abundance. This first dotted line corresponds to dark matter of 1 MeV, so 10 to the minus 3 GeVs, 10 to the 3, 10 to the 9, and 10 to the 15, the solid line. So just to show you that the primordial black holes can radiate the whole observed dark matter abundance, basically no matter how heavy dark matter is. Here I'm just adding 2 more constraints. So here in this greenish region, dark matter is always abundant. And here in this purple region, I have to be very careful because dark matter, if dark matter is lighter, say that 30 GeVs or so, I could have troubles with hot dark matter. So dark matter will be relativistic at the moment of structure formation. Okay, so that's the paradigm of dark matter emitted by primordial black holes via Hawking radiation, and with dark matter with only having gravitational interactions. However, the picture could be much complicated. For instance, I'm also assuming that dark matter has no self-interaction, so no sizable self-interaction. Okay, and now what happens if that's not the case? If dark matter only communicates to the standard model via gravitation. However, what happens if dark matter in the same scenario has sizable self-interaction? Okay, so in that case, the scenario could be much complicated. For instance, that dark matter could thermalize within itself, so it would be characterized by a temperature, which in general is different from the standard model temperature and the temperature of the black hole, of course. But also you can have number changing interactions, for instance, to the 3, to the 4. We can have dark matter reproduction, we can have cannibalism. So for instance, that can happen if I have scalar dark matter with just a simpler quartic coupling. So I can have elastic scatterings, I can have dark matter reaching kinetic equilibrium. And also with the same quartic coupling, I can have number changing interactions. So chemical equilibrium. So in this case, the question is not before for computing the dark matter abundance, what's the PBH dark matter abundance, and how many dark matter particles are emitted per black hole. Here the question changes. So now the question is, what's the energy density transfer from PBH to dark matter? Also, what is the dark matter temperature in the case dark matter reaches kinetic equilibrium? And what is dark matter equilibrium number density if they reach chemical equilibrium? As I was telling you, here you can have the scenario where you have reproductive dark matter or cannibal dark matter. So actually self-interactions are very efficient in this case, because what we have is that kind of suppressed production via PBH because it's Planck suppressed, right? So it's very inefficient, it's gravity, right? But dark matter will be very boosted, so will be ultra relativistic, just because at the end of their life, PBH have a very small mass, so they're very hot, so they're radiating very ultra relativistic dark matter. So the effect of self-interaction will be increase the dark matter density by the price of decreasing their mean dark matter kinetic energy. So self-interaction will trade kinetic energy into mass. So we're trading a few super relativistic dark matter, so into a big number of non-relativistic dark matter particles. That's it. So for instance, here I'm showing you basically the same parameter space as before. Now for a mass of 10 MeVs. So this dotted line corresponds to the case without self-interaction. this is dotted without self-interaction. And when I turn on the self-interaction, I'm moving this dotted line to the solid line, which corresponds to the case with self-interaction. And this is a model-independent result in the sense that I'm only assuming that I have self-interaction that are changing the number density because dark matter is reaching chemical equilibrium with itself. So as you can see, the dark matter production becomes much more effective in the sense that smaller beta could be explored now. Also, dark matter cools down, and therefore the key KV dark matter becomes viable, which was not the case in the case without sigma interaction. And just emphasizing that this is a model-independent result, right? So here I'll show you first the 10 MeV case, but also the 10 KV, 10 GVs, and 10 TVs. And as you can see that we're going from the dotted line without self-interaction to the solid line with self-interaction. And also, for instance, this case of light dark matter in the KV ballpark becomes viable. Okay. Okay, that was one point. That was the only one that I want to tell you. Now, what about other purely gravitational processes? So the Hawking radiation via primordial black holes is one purely gravitational process. Now there are other ones, for instance, the gravitational UV freezing. So, but before that, let me just show you exactly the same result, but just in another projection in different parameter space. So on the left here is exactly the same result that I showed you before, the same parameter space, beta as a function of the initial mass of the primordial black hole. And here I'm showing you exactly the same information, just projected in another plane. So here on the y-axis, you have the initial mass of the black hole in grams. And on the x-axis, I'm showing the dark matter mass. And again, the same constraints, CMB, BPN, underproduction, hot dark matter, overproduction, blah, blah, blah. So here, the information we are getting is that in all these white parameter space, I know how to produce the whole dark matter Ehrlich abundance for different values of the dark matter and different values of the primordial black hole initial mass for a given value of beta. I don't know which one, but it exists one value of beta for which I can produce the whole dark matter abundance. Just to emphasize that the typical parameter space here corresponds to heavy dark matter, 10 to the 10, 10 to the 14, 10 to the 6 GV, and high temperatures, 10 to the 15, 14, 13, right? And this maybe reminds you of another dark matter production mechanism, which is also inefficient. However, it could be the dominant in the same parameter space where you have heavy dark matter and very high reheating temperatures, which is what is called the gravitational UV freezing, right? So the gravitational UV freezing is just an example of the ultraviolet freezing, so the ultraviolet mechanism, where the dark matter is produced out of the standard model bath. So you have a collision in the early universe of standard model state into a couple of dark matter via the F-channel exchange of a standard model massless graviton. Yes. And again, okay, this process, of course, is unavoidable. It's gravity, right? So this massless spin 2 guy that couples with a coupling proportional, couples to the energy stress tensor. So it's possible to compute such a processes, and it will depend on the dark matter mass and the spin, and basta. Of course, also in the reheating temperature, right? So if you want the maximal temperature reached by the standard model thermal bath. And just want to emphasize there are no free couplings in gravity. So the only coupling, if you want, the only coupling is the Planck mass, which is fixed. So you can compute this abundance, and it will go in this way, so proportional to the dark matter mass and to the reheating temperature cube. In the case of this instantaneous decay of the inflaton, where T reheat is really the maximum temperature reached by the thermal plasma. So here I'm showing you a plot of T reheat and the dark matter mass. And here on the border of this triangle is the parameter space where I can reproduce the whole dark matter abundance. Here inside that overproduces, so I want to avoid this space because I'm overproducing dark matter. And this again, even if it's Planck suppressed, is very inefficient. It could be dominant if dark matter again is very heavy, and you have very high temperatures. So exactly the same parameter space favored by primordial black holes. So here I'm just putting everything together. So the gravitational dark matter production, when I'm taking into account, well, simultaneously PBH and gravitational UV freezing. So here, so these lines, CMB, blah, 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 is the same as before, PBH. And here I'm showing you the constraint coming from gravitational freezing, right? So just to say that gravitational UV freezing strongly constrains super heavy dark matter radiated by primordial black holes. Okay, that's what for the case where T reheat is exactly T initial, so that all black holes are produced exactly at the onset of radiation domination. However, here I'm showing two other plots, but I'm taking T reheat to be 10 to the 16 and T reheat to be 10 to the 14 GeVs. So just to emphasize the same point, that if you take dark matter that only interacts gravitationally, you have to take into account all possible channels. For instance, and here I'm taking focusing on PBH and UV freezing, just to emphasize that the constraints are complementary and that put strong bounds on the parameter space. Okay, okay, we have 5 minutes. Okay, so far I've talked about super heavy dark matter in particular. So again, 10 to the 16, 10 to the 10, 10 to the 14 GeVs or so. What happens in the other case if you take super light dark matter? For instance, if you take Axion, or in particular QCD Axion, the actions, of course, cannot be produced via the Wien mechanism. However, they can be produced in the early universe via the so-called misalignment mechanism. So where the initial, I mean, the key point is the initial misalignment angle. So it can have this kind of flow where it has the misalignment angle required in order to produce the whole QCD dark matter abundance, where MA corresponds to the mass of the action in electron volts, and F corresponds to the Peche-Quinn scale. So and this red line corresponds to the parameter space where you know how to produce the whole dark matter density in this misalignment mechanism, right? You don't know what this misalignment angle is. However, in the post-inflationary, you expect this angle to be around P over square root of 3. If it's in the pre-inflationary, you don't know what this angle. However, you expect it anyway to be order 1, right? So if you want an order 1 misalignment angle, that automatically means that the QCD action has to be in the ballpark of, say, micro electron volts, so 10 to the minus 6, 10 to the minus 5, or so, right? And now, what happens if you take actions, QCD actions radiated by primordial black holes? Okay, the first point, the dark matter is super light in this, so in the micro electron volt, ballpark. So they will not be, they're ultra relativistic, so they cannot be the cold dark matter. However, they will contribute to the dark radiation. So here, for instance, I'm showing a plot again of beta and the initial mass of the primordial black hole, and these contour lines correspond to the value of delta N effective. So 10 to the minus 1, 6, 10 to the minus 2, 10 to the minus 2, 10 to the minus 3. So it's still within the bounds, right? The maximum value of delta N effective, I think, is 0.2 or something like that. And so even if it's allowed, here I'm showing the future, what we expect will be the future constraint coming from next generation experiment, for instance, CMB stage 4. For Schwarzschild black PBH, or for a chair with a spin of 0.99. So one good thing is that it will be within the reach of future CMB stage 4 experiments. And now we'll have to go very fast. So even if actions radiated by PBH cannot be the dark matter, PBH can have a strong impact on the dark matter genesis via the misalignment mechanism. And why? Because PBH could give rise to a non-standard cosmological era, meaning that they could enhance the Hubble expansion rate, and they will also have an entropy injection when they evaporate. So for instance, here I'm showing the parameter space in red where you know how to produce the whole dark matter abundance, QCD dark matter abundance, if the axion has this mass of 10 to the minus 7 electron volts or 6 10 to the minus 8. Yeah, just 2 examples. So here again, I'm showing you basically the same parameter as before, parameter space, the misalignment angle as a function of the dark matter mass, the QCD axion mass. And again, the same as in the radiation domination, the axion, if you want the angle to be order 1, has to be in the micro electron volt ballpark, 10 to the minus 6 and to the minus 5. But due to the non-standard cosmology or non-standard cosmological era produced by PBH, we know now how to produce much lighter actions, how to reach much lighter actions due to the effect of this non-standard cosmology due to evaporation of primordial black holes. Okay, and I think they just have a couple of minutes, maybe one. So one slide, I think, now for the cases of ALPS. Here the effect is exactly the same. ALPS expects, especially super light ALPS in this. I mean, you can see this. My parameter space is, oops, where is my pointer? So 10 to minus 11 electron volts. So again, here ALPS cannot be produced by primordial black holes because they are super light. However, again, the PBH can have a strong impact on the production of the misalignment due to the non-standard cosmological era. And for instance, here this band corresponds to the standard cosmological era. However, this small band, the big one, corresponds to the case where you have PBH enter into the game. And I think I'm running out of time, so I just let you with my conclusion. So just to basically repeat the same thing, it's possible that matter only features gravitational interaction, and that PBH in that case formed in the early universe with very light masses, so in the ballpark of grams to tons. They will evaporate before BBN. They will have a strong. They were poorly constrained, and they could radiate the whole dark matter abundance if dark matter is basically heavier than MeV or so. That's the standard paradigm. However, the real life could be much more complicated. For instance, we have dark matter self interactions, and in that case, we'll have a boost of the dark matter energy density, and by cooling down dark matter. However, once we take into account this gravitational channel, we have to take all the gravitational channels, and for instance, the gravitational UV freezing, it's unavoidable. I will set strong constraints to the dark matter produced by PBH. And also now that's for light heavy dark matter. However, for light dark matter, you can have that even if they cannot be radiated by black holes. I mean, the radiation by black holes could not be the dark matter. They will contribute to dark radiation within the reach of next CMDS4 experiments. And the non-standard cosmology, due to the presence of these dark matters, will have a strong impact also on light dark matter. For instance, you have Axion dark matter or ALPS. And could be also in the read of future experiment like Clash, ADMX, DM radio. And that's all. Thank you very much.
Okay, thank you. Questions?
I have a question. You assume that the primordial black holes are somehow produced in the early universe. Do you know? Do you have a particular mechanism to produce primordial black holes in the first place?
Yeah, no. Here I was kind of skeptical about how they are produced. I was just assuming that they are produced at some moment in the early universe, and that they are monochromatic. That's true. That's something that I'm assuming. Of course, I don't expect this to be like super realistic. If you want to, what you can do is to take like a realistic model for the production, how this density fluctuation evolves, and then you can compute like the real I mean, this mass distribution. I mean, not assume them to be monochromatic, but yes, it's true that at this point you assume all to be monochromatic. Yes.
Thank you.
Thanks.
Chung-Ang, have a question?
Yeah, I'm thinking, yeah, I have a question about the axion. So what happens if axion actually decays to photons in your scenario?
Well, they will decay, right? They will decay to photons, to gluons. There's no problem.
Mhm.
However, their lifetime is typically super large compared to the age of the universe. So there's no real new features here. Here's exactly if you see the action, so no difference for the standard scenario.
Yeah, is it still true to contribute delta N effective only? I mean, even axion decays. Or maybe it's true.
I don't. Yes, I mean they can decay, but if their lifetime is super large, I don't see a problem. But maybe I'm missing your point.
I was thinking shorter lifetime.
Okay. No, here I really want dark matter to be, I mean, the actions to be dark matter, so with a very long lifetime.
Oh, you take axion as the dark matter. Okay.
Exactly. Yes. And that's guaranteed because I'm taking actions here to be, I mean, where is it? In the
but in general,
range, they're completely stable. Well,
yeah.
They really care, but they're stable.
Yeah, let's think of a more generic ARF case, and that ARF may or may not be the dark matter. Then, here you consider the axion photon conversion. So, okay, so here ARF doesn't contribute to delta N effective, for instance.
Yes, they're contributing always at the same amount. Here, what is it? Yes, typically more than 0.1.
Okay, thanks.
In the paper, we have an equivalent plot, but I just didn't put it because it's very similar.
Okay, yeah, thanks.
Actually, let me give you a comment. Maybe you can answer some question. I mean, yesterday there was a talk on hot actions, and Francesco Deramo gave a talk about that, and he assumed that the action abundance is zero at the initial temperature. It's like reheating temperature. So if your primordial black hole story is correct, then we need to modify that story. I mean, although you assume that maybe, I mean, your production mechanism is independent of the action coupling to the standard model particles. But somehow, what if you have a size of coupling between action and the standard model? Like if you make the action to be hot action, and I mean, do you have any comment on that? I mean, I don't know if you have followed my question. What?
Yes, it's true. Here, actions radiated by primordial black hole would be super relativistic, just because, especially at the end of the PBH life, they're super hot. So action would be super relativistic.
Because I'm saying that you can produce action from the decay of radiation of the primordial black hole, and you can also produce action from the thermal scattering in the standard plasma.
But that's typically subdominant with respect to this population radiated by primordial black holes. Yes, for instance, you can produce them for sure via gravitational scattering. So this UV freezing. Exactly, gravitational freezing, but that's subdominant. Yes.
Okay, maybe.
Okay, so we have 2 more questions. First, Poyen. Poyen, question?
When we cannot hear you.
Pyongwon?
Sorry, can you hear me now?
Yes.
Okay, yeah.
Sorry, yeah. Thank you for Nicolas, the interesting talk. I would like to ask, the beta is the energy density between the primordial black hole and the standard model energy density, right? So it's
the moment of production.
Okay, so
it's not it's not really well defined because it's not a redshift invariant. So you have to be careful when you define it. Yeah.
Okay, so with this amount, you can generate the diametrically abundance.
Exactly. Yeah.
Okay, I see. Yeah, thank you.
Thanks.
And Professor Ko?
Yes. Hello, Nicolas.
Hey.
Nice talk. Yeah. In your slide 12, page 12. No. Yeah, this slide. So, for example, if you look at the dashed lines, the slope changes in the middle. And could you briefly,
like here?
What is the qualitative reason for this change in the slope?
Yes. So let me remember. So here the point is that okay, yes, this change corresponds to the moment when the dark matter mass is the same as the initial PBH temperature. So yes, exactly. Now I don't remember which one is the site, but exactly. But this change of slope here for sure, for instance, here, and here corresponds to the moment where M dark matter, so the dark matter mass is equal to the T black hole initial. Exactly. So if dark matter is lighter than the initial temperature of PBH, that means that it could always be radiated during its whole evolution. Right? However, if dark matter is very late, is very heavy, it could only be radiated at the latest stage of PBH evolution, of its lifetime.
Okay, thank you.
Welcome.
All right. So thank you, Nicolas.
Thank you very much.
Okay, so now we have a break until 11, right?
Yes.
Okay, see you soon.
Okay, see you.
Kwon with Hitoshi Murayama, please.
Okay, so thank you for having me. I see so many friends in the audience, which is wonderful. And too bad that we can have the in-person workshop, but of course, hopefully we can be back in that mode starting the summer or so. So I'd like to tell you about the fun I've been having with this idea that the dark matter may be a composite object in sort of QCD-like theories. I've been actually fascinating about this for several years by now, but there's something new I wouldn't tell you today. So that's the content of my talk. And I don't need to tell this audience that the range of parameter space for dark matter is huge, at least spanning over like 80 orders of magnitude between the primordial black holes we just heard about all the way to fuzzy dark matter. And in between, there had been many, many different ideas of dark matter candidates, and I can't do any justice to any of these. But my talk today is actually in this range, talking about dark hadrons. And why am I fascinated with this idea? Well, first of all, QCD is a beautiful theory and arguably the most beautiful quantum field theory of its kind. And why not nature using it again? And especially when you're interested in self-interacting dark matter, that was also mentioned earlier today, then you would like to actually have a large cross-section and relatively light dark matter. And for this purpose, a dark QCD-like theory is perfect. And also, especially for the accommodating the constraints from the cluster scale versus what you need from the dwarf galaxy scale, you may need a velocity dependence of the self-interacting cross-section. And for this purpose, I proposed some time ago that the resonance is actually a beautiful way of achieving a velocity dependence. And resonance, of course, is very common in dark QCD, so it can provide that. It can also be combined with this idea that dark may be asymmetric. So in this case, the dark matter have to shed symmetric component. And once again, thanks to a large cross-section, that's easy to do for dark QC-like dynamics. So having a viable model of asymmetric dark matter, again, QC-like theory is kind of perfect for that purpose. And you might also want to use the QC-like dynamics for the hierarchy problem. That was the idea of Technicolor. And to be totally honest, when I was back in grad student, I like Technicolor far more than supersymmetry. And of course, unless if it hadn't had phenological issues, that would have been a beautiful idea. And maybe baryon asymmetry is also due to some kind of dynamics like that. So there's many reasons that QC-like dynamics might be used by Mother Nature, not just once, but more than once, twice, 3 times, whatever. And especially using the self-interacting dark matter as a potential motivation for it. And again, this audience knows very well that there is some issue with the simple cold dark matter paradigm. And some of the profiles of the densities in dwarf galaxies might be actually explained better if the dark matter is self-interacting with the typical cross-section over mass. Let's say that's on the GeV range. The cross-section turns out to be of the order of a barn, which is really the size of strong interaction cross-section we know in the standard model. So that kind of the strong interaction might be actually necessary. And of course, by now, it's not just a core cusp problem, because some of the dwarf galaxies even show actually cusps, but there is actually a large diversity in the density profiles from one system to another. And that diversity might be explained the self-interacting cross-section. This issue is far from settled because the baryonic feedback can flatten the density profile near the center of the dwarf galaxies. So this issue is certainly not settled, but hopefully we can learn something about that. So one of my projects is to mount a new spectrograph on the Subaru telescope, and the Subaru is 8-meter telescope, so you can actually observe very faint systems. So we can actually study ultra faint dwarfs, and in this case, you do not expect any baryonic feedback at all. So you see really plain vanilla distribution of dark matter without the baryonic feedback. And also in some of the larger systems where you do expect baryonic feedback, that should leave imprint in the metallicity distribution of the stars in the system. So we will learn something in that case too. So that's the project that is ongoing. It's a very complicated instrument. The wide field corrector lens system already exists because the imaging survey using a camera called Hypership Prime Cam. That may be the largest CCD camera in the world right now. And we have the system of these little robots that can control the direction of the optical fibers within 10 micron or so. And we have just built this prime focus instrument. And it's a complicated lens system, has to do with this in fiber system. Here's the camera and assembled in the spectrographs. Metrology camera had been already installed. And then this is the first installed the spectrograph. The fibers have to be bundled in these tubes so that there wouldn't be actually tension building up that might degrade the optical property. Assembly of the camera, and this is the assembly of the fiber positioner. So it's actually coming together quite substantially these days. And we hope to start the survey in early 2024. And one of the aims I mentioned earlier already is to map out the density profile by measuring the radial velocity of stars in dwarf galaxies. And Bode's 1 is actually one of these ultra dwarfs. So we get some insight into the cosmological history, evolution history of these dwarf systems, and hopefully we learn something about the nature of dark matter itself. So this is an area where we can expect to see some the advancement in the near future. And to describe the self-interacting dark matter, what used to be the case is that everybody solved the Schrödinger equation and worked out the scattering cross-section as a function of various parameters, like in the case of the Yukawa potential, and which is actually quite cumbersome and sometimes rather complicated. And I just learned a few years ago that Hans Bethe already solved this problem back in '49, and his theory is called effective range theory. The idea is to parameterize the scattering, the phase shift in the scattering in this power series expansion in momenta k. So it turns out that this combination k cotangent delta is the phase shift of the scattering, is analytic in momentum and has an even function. So it starts with a constant term, that's nothing but the scatter length. That's the term we normally keep in any of these low energy scattering cross sections. But now that we're interested in velocity dependence, you need to go to the next order in expansion. And this RE is what is called the effective range that roughly corresponds to the range of the force that will lead to this cross section. And for most purposes, we don't need to go to the k to the 4th. So this is actually a parameterization which is guaranteed to be unitary, which is actually not trivial if you actually go ahead and solve the Schrödinger equation to get the correctly unitary cross-section, because the perturbative calculation doesn't give you unitary cross-section. It has to be always compensated by high-order terms that give you imaginary parts. And so getting unitary cross-section is actually fairly non-trivial in perturbation theory. But in this the effective range theory, you are describing this phase shift directly. And phase shift, of course, is unitary because S matrix, the e to the 2I delta. So by definition, that's unitary. So that doesn't give you any theoretical issues. And so this is actually fully unitary and non-perturbative description of any low energy scattering processes. And that can be applied not just to S wave, but also P wave and higher order waves. So this is actually an ideal tool for simulations and phenomenology of the low energy cross sections needed for the self-interacting dark matter. And once you have this tool, it's easy to see that you can actually have a resonance described by this, or also near threshold bound state, just like in the case of deuteron in the neutron proton scattering cross-section. And if you have a resonance, it's easy to see that you do expect substantial velocity dependence in a scattering cross-section, because if you have a resonance just above the threshold, and if you have a system with a low velocity profile, like in dwarf galaxies, you might hit the resonance quite often. But if you go to a system with high velocity profile, like in the galaxy clusters, then you would not hit the resonance most of the time. So the resonance would contribute to the cross-section only in systems with low velocity profile. And even if you have the resonance, if you go to really low velocity profile systems, you again start not hitting the resonance. So you see some kind of peak in a cross-section. And indeed, if you work this out, you see a curve like this orange one. So in system with high velocity profile, you're not hitting the resonance, so the cross-section is low. If you go to very low velocity profile, again, you are missing the resonance. It's a low cross-section, but somewhere in the middle, you have sort of the ideal velocity profile to hit the resonance very often, and you have an enhancement in cross-section. So this is the way that you can get this velocity-dependent cross-section, which is really needed for the case of the self-interacting dark matter. It turns out that even if the resonance is actually below the threshold, namely it's a bound state, that will still affect the scattering cross-section because of the pole in the S matrix elements. And that can give you a profile that looks like this dashed line. So even below threshold, the bound state can affect the scattering cross-section and gives you the desired velocity dependence. So using this technique, you can fit the data and you see that what kind of mass range will give you the correct density profile, the velocity profile of the scattering cross-section. And in the case of P wave, you see that mass will be fairly light, less than 7 GeV or so. On the other hand, if you go to S wave, you can accommodate much higher masses, even up to 40 GeV or so. And if you're looking at this range, that's still considered to be relatively light compared to a typical WIMP dark matter. And it turns out that the standard freeze-out scenario doesn't work. So if you, for example, look at the S wave cross-section, the unitarity limit says the cross-section has to be limited by this. We know what the velocity dispersion is, V, and only when mass is light enough, you can accommodate large enough cross-section. So we typically need something like 14 GeV. You have already seen a number like 7 and 20 in particular. So that's the range we are interested in. So the dark matter has to be relatively light for this purpose. But there's a limit from the CMB that the scattering surface gets a little bit blurred if the dark matter annihilation is happening at the time of recombination. That already restricts the mass of dark matter to be higher than 20 GeV or so. And if you take the limit from the gamma ray from the galactic centers seriously, then annihilation of the dark matter requires the mass to be bigger than 300 GeV, assuming the standard freeze-out scenario where you know the annihilation cross-section. So the standard freeze-out doesn't work for this kind of idea of the self-interacting dark matter. So there are several options, and we're talking about all of them today. One of them is SIMP, where the freeze-out happens from 3 to 2 annihilation process instead of 2 to 2. Dark matter may be asymmetric, and I will talk about that. And it may not be freeze-out, but rather freeze-in. And yet another possibility is to avoid the dark matter annihilation in the halo or CMB by assuming that the charged dark matter state would downscatter to the neutral states. And so I will mention all of these 4 scenarios today. So that's the content of my talk today, basically. And because I'm talking about the QCD-like dynamics and dark sector, there are basically 2 types of candidates which might become dark matter. And one of them is basically pion-like states, namely meson-like states of the QQ bar type. The other possibility is the baryonic states like protons and neutrons. So let me get started with the dark pions first. And the last half of my talk today would be on the dark nucleons. Okay, so just reviewing the WIMP miracle. So in this case, we're talking about this 2-to-2 annihilation process from the 2 dark matter particles annihilating into 2 standard model particles. And people love this idea that the typical mass expected in this case would be about 300 GeV, which is really the electroweak scale, where we expected to discover new particles such as supersymmetry in extra dimensions. And so the community got fascinated with this idea of linking the dark matter to the hierarchy problem. But as we all know, there's no sign of such states at the Large Hadron Collider. We don't see WIMP-type particles in direct detection sources as well. I already mentioned strong constraints from indirect sources. So we started to actually look elsewhere these days, and there's a proliferation of new ideas on what dark matter may be. And one of them was actually the SIMP, going through 3-to-2 annihilation. So what's sometimes called cannibalization, because dark matter self-eats itself, hence cannibalism. And in this case, you expect much lighter dark matter by almost 3 orders of magnitude in the range of 300 MeV. That's really the energy scale of the strong interaction indeed. And you are relying on rather strong interaction to make this 3-to-2 process happen. That would really require the strength of the coupling to be order 4 pi, hence again, the strong interaction. So that this 3-to-2 process is what is usually called the strongly interacting massive particles, and SIMP. That goes back to this original paper. And what I added to this story is that it turns out that dark pions are perfect for this purpose, because the dark pions would obey Cairo-Lagrangian. And Cairo-Lagrangian for many coset space would actually have this Vesumino-Witten term. And Vesumino-Witten term is nothing but 5-point interaction among the pion states. So satisfying some topological constraints in the coset space of the symmetry breaking, you can really have this 3-to-2 interaction by fiat. So you don't need to put it in, it's already there for any pions of this sort. And that would really lead to this cannibalization of 3-to-2 process. So the idea was that you have QCD-like theory with the massive quarks. I assume them to be degenerate. And if the theory confines, then you have the low energy theory of the pion-like states, the QQ bar pseudoscalar mesons, and they follow the Cairo-Lagrangian perturbed with the quark mass term. But again, we have this Vesumino-Witten term. And if you write them in components, then you have the kinetic term, mass term, quartic interaction, and this quintic interaction that will lead to 3-to-2 annihilation. And by going through numbers, you can see that indeed the mass range of 300 MeV would satisfy both requirements, namely for getting the correct abundance in solid lines versus satisfying the limit from the self-interaction in the cluster scale. You have to be below this line. And in this thickest band, you satisfy both requirements. So it actually works. And that's not limited to the SPN gauge theories, SUN gauge theories, but also to SON gauge theories. And story is pretty much the same for any of these gauge theories. But coming to the specific idea of getting this resonant self-interaction, you have to wonder whether such a resonance is natural in QCD-like theories. And Yu-Dai was the first speaker today, and we walked to him on this question. And it turns out that there are many resonances in QCD where resonance is really, really close to the threshold. The famous example is the phi resonance, which is this SS bar bound state in a vector resonance, 1-, and that's really at the threshold of K plus K minus. So in this case, that's kind of natural, because if you think of the quark mass to be somewhat heavy, then K plus contains one strange quark, K minus contains another strange quark, and phi mesons is SS bar contains 2 strange quarks. So roughly speaking, this meson-meson state is twice the mass of the quarks. This vector resonance state is also twice the mass of the quarks. So they can be similar to each other without fine-tuning. And of course, getting really at the resonance requires some level of fine tuning, but it's already close to begin with. So it's kind of natural. And indeed, many of these states can be worked out, for example, in lattice calculation. And twice the pseudoscalar mass can be close to the vector mass. And this kind of resonance is very common in various versions of nuclear physics as well. So QCD is actually full of such cases. But in this case, you're talking about a pseudoscalar hitting a resonance of a vector meson. And it turns out that because the vector meson has to be in a p-wave resonance, and you have seen that it has to be limited to the mass range below 7 GeV or so. So the parameter space is actually quite limited if you would like to put that together in a realistic model, together with a mediation mechanism such as a dark photon. So it turns out the parameter space is very limited, it turns out. And back then, when we were working on this together, then we didn't know actually some simple nuclear physics I learned actually just the last several months. It turns out that in addition to these pseudoscalars and vector mesons we know and love in QCD, there are actually more. And in these pseudoscalar and vector cases, we know that they form an SU3 non-net. And that's because they satisfy the famous Gell-Mann-Okubo relation among their masses. For the pseudoscalar mesons QQ bar, the kaon mass, pion, and eta masses actually allow you to form these combinations. And Gell-Mann-Okubo relation tells you that this 4 times kaon mass squared has to equal to the mass of eta pion squared plus 3 times the mass of the eta squared. And you see that numbers actually work out quite similar to each other within a few percent of accuracy. And getting anything within a few percent for strong interaction is really amazing. So this is really a good way to observe that indeed they form a SU3 non-net. And of course, you know the pion is light because there's an Goldstone boson. Eta prime is heavy because of this U1 anomalous instanton contribution to its mass. So in this case, you don't need to include eta prime for this mass relation, and it does work out. In the case of vector mesons, it's a little bit more complicated because it's phi and omega mesons are the linear combination of singlet and octet. So by taking linear combination between them, you need to extract the octet component of the vector meson mass squared by this linear combination of omega mass squared plus twice the phi mass squared. That's the octet combination. But apart from that little subtlety, they satisfy the same Gell-Mann-Okubo relations. Again, you see a even better than a percent level accuracy. Again, a percent level accuracy of agreement between these two numbers. And what I learned in just the last several months is that we used to think that that's it for the low energy hadron spectrum, but now it's considered that these 0+ states, namely scalars, are actually experimentally well established. So I grew up in a time and back in grad school that the sigma meson didn't exist. It was not a particle data group. It was highly controversial. And that's why people integrated out a sigma field. So linear sigma model was considered to be only a toy model of spontaneous symmetry breaking. What you have to really use is nonlinear sigma model because sigma state doesn't exist. That's the same thing as chiral Lagrangian. So in some sense, sigma was just the hypothetical idea. But now, given the wealth of data, especially from the heavy quark physics, where some heavy mesons can decay into pi-pi final state, and people have observed clear peaks in pi-pi invariant mass. So this F0 500 aka sigma is now considered to be well established. And even lattice calculations confirm the 500 GeV sigma type meson. And not only the sigma, but also this whole non-net of the scalar mesons these days. And once again, they satisfy the Gell-Mann-Okubo relations. So you can see that the entire non-net exists together with F0, which is the singlet component. So these states are really there. And I just learned this, as I said, only a few months ago. And interestingly, one of them, if you look at this state here, called F0 1000, or 980 actually, or A0, and these states are really at the KK threshold. So if you look at the KK scattering in S channel, they actually go through these resonances, which is right at the threshold. And that's exactly the kind of situation we need. And once again, these states are now well established. And that's what I actually working on with these people now, together with a new student, Dan Kondo. So these near resonance states are very interesting. And these states actually considered to be not QQ mesons, but rather tetraquarks or meson molecule. And the idea of tetraquark goes back by an old paper by Bob Jaffe in, I think, 70s. I know before my time, so I don't really know. The idea is that tetraquarks are bound states of two diquarks, and diquark is the QQ bound state of some sort, and QQ bind together in S wave, and it's both antisymmetric in flavor and color. So QQ state is actually 3-bar in color, and also 3-bar in flavor. So UD state would act as if it was anti-strange quark, or anti-strange scalar quark rather, because they together form a J equals 0 state. And those scalar bound states form further bound states into color singlet state, and that's the idea of tetraquarks. And that sounded very exotic, I'm sure, back in those days. But now we do see tetraquark states in B physics and D meson physics. So these states are now known to exist. And it turns out that they exist already at this very low energy spectrum of the hadrons. And especially these states, which are very close to threshold, can also be considered mesomolecule. So it's sort of a loose bound state of K plus and K minus, or K naught and K naught bar. Which picture is right is in some sense a well-defined question, because you expect the continuum possibility interpolating these two limits, sort of like the BEC-BCS crossover in cold atom physics or condensed matter physics. So we can't really tell these concepts apart from each other. So both of them are, I would say, equally valid. And especially when you take this limit of meson molecule, you do expect this kind of scalar meson to be really there at the threshold of the scattering. So in some sense, this is actually revenge of sigmas. Linear sigma model is now right, and we can use it to study phenomenology of these low energy hadrons. So now that we equip this new idea that linear sigma model is actually not crazy to talk about, we can talk about the interaction between the standard model and dark QCD. And I focus on the vector portal today to this kinetic mixing between dark photon and photon. But of course, there are many other portals we discussed, and some of them I even involved too, together with Hyun Min, for example, who is the organizer of this meeting. So there are many other possibilities, I'm sure there are, but today I focus on the vector portal. So idea is that dark QCD couples to dark U1. So some of the dark quarks are charged under dark U1, and so that some of the bound states are also charged. The simplest group I talked about with Leonid and Eric is the idea of SPN gauge group, or SU2 is the simplest case, and with the 2 flavors. So 2 flavors for SUN2 gauge group means 4 doublets to avoid Witten's anomaly. So there's an SU4 flavor symmetry, which is isomorphic to SO6. And you can gauge U1 subgroup of that, which is embedded inside SO2, which is part of the SO5 subgroup of this SO6. So that way, I'm assigning basically 2 positive charges to 2 of the quarks, 2 negative charges to the other 2 quarks, and their bounces have now this spectrum of 2 doubly charged pions, and isotriplet of the neutral pions, and this isospin SU2 is exact because of the quark masses that they generate. So I used to think that this is actually a SU4 mod SP4 Cairo-Lagrangian, but now that there is also the sigma field, this is really the linear sigma model of SO6 broken to SO5, like what you find in textbook. And this sigma particle could really be at the threshold of this pi-pi scattering resonance. So in this case, it turns out that even for the self-interacting dark matter, even the WIMP can have a revenge. This actually follows because of this downscattering I mentioned earlier. So it is kind of WIMP because the freeze out happens because of the annihilation process of the charged pions going through the dark photon that mixes to our photon going to the standard model FF bar. So that's how freeze out happens. But we have these charged and neutral pion states. So after the freeze out is over, we know in Cairo-Lagrangian, charged states is always a little bit heavier than the neutral states because of the electromagnetic correction, and they are strongly interacting. So in the remaining thermal bath, these charged states would scatter into the neutral states because neutral states are a little lighter. They are very close in their masses, the electromagnetic correction is typically small, but nonetheless, lighter states are always preferred at the final state of the scattering process. And this is a downscattering I mentioned earlier. So after the freeze out, without doing anything, all the charged states will disappear, and what remains is only the neutral pions as the dark matter of the universe today. So what that means is that direct detection limits and indirect detection limits just simply go away. So even though this is actually WIMP-like, it turns out that this is viable thanks to this downscattering. And if you go through the math, you find that this range of the mass is actually preferred for this scenario. And you can see the prominent space is fairly wide for the mass of the dark photon. And for this plot, I specifically chose the mass of the dark matter to be 16 GeV, which is the sort of the central value for the S wave, the self-scattering process. And so this is actually viable. On the other hand, you can have an even simpler scenario by using the SU2 mod SO2, which is SO3 mod SO2 linear sigma model, which is just two-dimensional sphere. In this case, you use SON gauge theories with two flavors, and you have one quark with charge 1, one quark with charge -1. They bind together to form only two meson states, pi plus plus and pi minus minus. But again, this is a linear sigma model, so the sigma state, and altogether, this is a triplet of SO3. So in this case, the states are charged, so they cannot be the freeze out scenario. But if you do freeze in, the kinetic mixing can be actually very small to get the correct abundance, and you can avoid both direct and indirect detection in this case, so it actually works. So it turns out that even for this very simple idea of dark pion being the self-interacting dark matter, you can get resonance thanks to the fact that now we know sigma actually does exist in QCD, and you can find very simple gauge theory actually that achieves this kind of scenario. So that's about the dark pions. And the rest of the talk is about dark nucleons instead. In this case, to make the nucleons a dark matter, we are talking about asymmetric dark matter. And of course, the idea that the baryon density of the universe and dark matter density are different only by a factor of 5 or so, even though if they may be coming from a totally different origin, is considered to be a big coincidence problem. But if this is also asymmetric dark matter, maybe there's a connection between the asymmetries between the dark matter and our baryons. So maybe you can understand this coincidence as well. So that's the idea of asymmetric dark matter, which has been, of course, discussed in literature over the many years. And for this kind of idea to be viable, you need to efficiently get rid of the symmetric component so that only the asymmetric component remain at the end of the day. So the sector, the rather be strongly coupled. So that means that you're talking about, again, some strong dynamics, maybe QCD-like. Then you're talking about things like the dark protons and dark nucleons. And if the asymmetry is the same between the dark matter and our baryons, namely 10 to the -9, then you would expect the mass of the asymmetric dark matter to be sort of 6 GeV-ish. And in order to explain the existence of asymmetries, just like in the standard model, you have to rely on anomalies. But gauge theory, of course, has to be non-anomalous. So having a non-anomalous gauge theory that can accommodate anomalous baryon or lepton numbers really speaks for something like the standard model-like structure. So in the end, you would like to have the standard model for our theory and another standard model like gauge theory for the dark sector. And they are connected in such a way that you can transfer asymmetries between them. And that's simply achieved by the neutrino portal. So that's the idea I'm going to talk about. So we have the standard model and we have the dark sector. By connecting these two sectors by the neutrino portal, you can transfer the asymmetry in leptons from the standard model to dark sector and vice versa. Then they can equilibrate between the sectors, and then they share the same asymmetry. At the end of the day, that will lead to a dark nucleons to be the asymmetric dark matter. And of course, once you have the standard model-like structure, you can connect them also through the vector portal, just like what I discussed a few minutes ago. You can also go connected by the Higgs portal, which I discussed with Jun Min and company in other scenarios. So that's how you can actually think about how a dark sector might look like. So for simplicity, I'm just depicting the case with only single generation of SU3 equals SU2 equals U1 in the dark sector. In case this sector is actually slightly higher, it might do sort of the electroweak-like phase transition that will lead to the generation of the baryon and lepton numbers. And I'm assuming that heavy lepton, like tau lepton, plays a role of top quark bouncing the bubble walls in the first sort of phase transition. And that way you can generate baryon and lepton numbers by the same amount from the electroweak sphalerun process. But through the neutrino portal, only the lepton asymmetry gets partially converted to the standard model. So you have less lepton asymmetry in the standard model now, which further gets converted to baryon asymmetry in the standard model, which is even more suppressed. So it turns out that the baryon asymmetry in the standard model is quite a bit smaller than the baryon asymmetry in the dark sector. And if you go through the math, in the end, the up and down quarks in the dark sector would form the mesons and baryons. Symmetric components would really quickly get annihilated because of strong interaction. And some of the pions have to decay to avoid the ineffective in this theory. But through this vector portal of the kinetic mixing, and they would just easily decay into E plus C minus into the standard model. So what remains in the dark sector in the end is whether it's a dark neutron or dark proton, depending on the mass spectrum. In the case of dark proton, which is charged, then it has to be accompanied by dark charged pion to have a neutral dark pool in the end. So you can have a variety of scenarios. And how to transfer asymmetries is just written in this, and that will give you an estimate of the dark neutron depending on the order of the phase transitions. So it's in the 1.5 GeV range. And once you have these dark nucleons, they might have this velocity-dependent cross-section, just like we actually do in QCD between the two neutrons in the standard model. And it's really amazing that the neutron-neutron scattering cross-section has size of whopping 30 bonds, which is almost 100 times bigger than the geometric cross-section of the neutron. And thanks to this near resonance-like states. It's actually not a resonance called the virtual state, but because of the pole just around the threshold, you can have this significant enhancement of the cross-section. And this is what can happen with a dark neutron. If you actually have a dark proton instead, then you also need to be accompanied by a charged pion, and pion proton can also hit the delta resonance. So in this case, that's an explicit resonance state. And we know that their masses are also pretty close in QCD. So they can indeed cross at some range of the quark masses. So this is the way you might also get this resonant self-interacting cross-section. But in this scenario, the neutrino portal is required, and there are some constraints coming from the lepton flavor, the lepton flavor violation, like mu to E gamma. There's also constraint from charge coherent universality. There's also constraint from exotic Z decays. So the range of the mixing angle is already restricted at the level of 10 to the minus 2 or so. These numbers are squared, so mixing angle itself is like 10 to the minus 2 or so. But there's still a large range that would achieve the equilibrium between two asymmetries. And so this will still lead to exotic Z decay, which may be detected in the future, the E plus C minus 6 factories like FCCEE or CEPC in China. In addition, the Higgs would also decay with this the Higgs portal because the Higgs can mix into the dark Higgs that might decay, for example, into two dark photons. Each dark photon would mix back to the photon and go to well-correlated low mass pi plus pi minus, mu plus mu minus, or E plus C minus. These things are actually very difficult to look for because of the conversion in the detector. But if you go to TPC like detector like ILD at ILC, then there's a low material in the detector. So there's not much conversion going on. And these states can be picked up very easily. So this is another potential signal. Or Higgs might decay into dark leptons in the dark sector, which may undergo the cascade decays. Then you're talking about the shower of these states in the final states. And that will be a very exotic way the Higgs decay. But this is also very difficult to pick up the Large Hadron Collider because of the high multiplicity in the final states. And this will be really the hallmark of the future, the E plus C minus Higgs factories, which actually have the sensitivity, which is 10,000 times better than the high luminosity LHC. So that's where I actually organized the workshop called IOCX last October, and we solicited many new potential ideas in addition to the central detector of the precision Higgs physics, but can also mount various beam dump experiment, extracted beams, and long-lived particle searches, even simulating black hole using the Schwinger field, high electric field that would lead to basically analog of the Hawking radiation. And these experiments can indeed be done in this linear facility, and I don't have to really time to go through all of these things, but one of them can lead to actually very good sensitivity searches for the dark photon, as an example, which is related to my talk today. So in the case, the asymmetry originates in the dark side, transport the standard model I mentioned earlier. I already said that dark matter mass is rather low, like 1.5 GeV. And if the dark matter is a dark neutron, then direct detection mounts don't exist because it's neutral. So there's a wide parameter space still there, but they can be covered by a variety of beam dump and LHC and also Bell experiments. And the next talk will be covering the Bell experiment, looking for sensitivity of dark matter searches like this one. And if you have the dark proton, of course, the constraint from the direct detection experiment is already pretty severe, depending on what the charge, the hyperstructure constant, fine structure constant of the dark sector may be. But still, there's some parameter space, and the future evolving of the dark matter searches will be actually very interesting to close this window. When the asymmetry actually originates in the standard model site, like the standard model electroweak symmetry, the various analysis, and the dark side has a smaller asymmetry in that case, and even though it's an asymmetric dark matter turns out to be actually fairly high, like 60 GeV. People haven't talked about this kind of heavy asymmetric dark matter before. In this case, parameter space is much, much wider because the dark photon constraint is weaker when it's heavier. But once again, the direct detection limit can be improved in the future. And interestingly, even dark neutron might actually have an EDM, because you could have the auto pi theta parameter in dark QCD, which is not restricted by data right now. So if the dark neutron has the EDM, you can look for that as well. So that's a kind of interesting possibility. And there can also be an interesting idea of dark spectroscopy I proposed with Univ and Eric. And the idea here is that if you do experiment like Bell, which we hear about next, then you can look for the monophoton signal, where you see this photon and measure its energy. And once you measure the energy of the photon, you see the mass of the recording system, which is in a one-to-one correspondence to the visible photon energy. So without seeing anything on the dark side, you can actually measure the invariant mass of the system and can perform a spectroscopy. And for example, this is just a mock-up of the charmonium type states in the dark sector, which might show up in Bell 2 experiment if you can do this single photon tagging. So in principle, you can tell what is the color of the dark sector, what is the gauge group, how many flavors, what are the quark masses, if you can actually do a fit to the data using lattice QCD calculation. And if the dark matter mass is on a heavier side, I mentioned like 60 GeV, that will be done at the IOC instead. And in addition to this kind of signature, you can have this the electroweak phase range in the dark sector, which can be a little bit higher temperature compared to the standard model. Then the gravitational wave can be in this LIGO frequency range. So LIGO, Virgo, Kagura can actually see gravitational wave signal in this case. In a case of the other case of the low energy 1 GeV kind of dark matter, then that can fall into this actual range, which may be probed by actually the Gaia and Theia satellite in the future. That's something we proposed with the Juan and Graham recently. So there's actually a fair amount of signatures you can look for, even though all the action is in the dark sector. So this is my summary. QCD is beautiful. Major may use it again. And that can actually solve various issues like dark matter and barrier symmetry, maybe even hierarchy problem, if you actually combine this dark standard model-like part sector with a twin Higgs actually theory. And it turns out that there are plenty of signatures from direct detection, indirect detection, beam dump, lepton flavor violation, IOC, Bell, and so on and so forth. It would be really exciting if you can do dark spectroscopy, that you can really see the signature of the dark resonances and determine the dark gauge group in principle. And you can have this resonance self-interaction in dwarf galaxies. And some of the interesting collider signatures would be rare Z and Higgs decays, and they may be accompanied also with a gravitational wave signal for various range of the frequencies. So that's the fun I've been having with the composite dark matter models. Thank you for your attention.
All right, thank you for the nice talk. Questions? Yu-Dai? Oh, Yon, yes.
Yeah, I've got one. Could you say a bit regarding the model of dark pion dark matter? What's the possibilities to probe that? You said direct and indirect detection doesn't work, but which of the
no, it does. So I didn't show it simply because the phenomenology is actually fairly common between them. So the idea is that you can look for this kind of direct detection if you have actually the charge states. Let's see, can I show this again? Yep. So this is the plot for the dark proton. But if you have a dark charged pion as a dark matter, which is possible in the case of the freezing scenario I mentioned earlier, then exactly the same kind of idea would apply. And it's a bit heavier. So the constraint is actually even more severe, which means that the future detection experiments have better chance of actually seeing it. So I simply didn't show a plot for this because, you know, it's just on the right-hand side of this plot, but the idea is very similar.
Okay, but how about
you can also do the same spectroscopy in E plus E minus experiments as well. Sorry, I interrupted you.
Yeah, sorry, me too, sorry. So what about the case where you said you've got the charged dark pions downscattering to the neutral dark pions, which then form the dark matter? And that sounded like...
So in this case, there is no direct detection constraints at all. So in this case, that's actually very difficult to do, but instead you can still look for dark photon though. And the spectroscopy, again, is principle impossible.
Okay, so we could hope that the dark photon coupling is in the range where we are, or in the mass is in the range where it's
Yeah, then you can see these bumps in the dark photon energy spectrum. That would be really fun.
Nice.
Like this. Okay, thanks for the question.
I have a
Anybody
question.
else? Go ahead.
Yeah, you consider the multi-component dark matter with the dark pion and dark neutron. And
dark proton.
Dark proton. So do you have any interesting features with multi-component dark matter?
Yeah. So the interesting feature is really that would also allow for the resonance, delta resonance. So when you have the pion-like state together with the proton-like state, then the proton pion can hit the delta resonance for the self-interaction. So this is really the case where having a resonance is also kind of natural in QCD dynamics. So that's the case. And also, if you look at the direct detection searches in the future, then dark proton and dark pion may have different masses. So you see, in principle, sort of the convolution of two different recoil energy spectrum. And so that depends on, for example, what the target mass is. So you need to have relatively heavy-ish the nuclei. So xenon for scan surface purpose, if you can rely on a middle type effect to extract the cross section, then you see basically the two peaks in the energy spectrum, the recoil energy spectrum, which corresponds to half mv squared for the pion and half mv squared for the proton. So that will be another very interesting signal to look for. Did I answer your question, Hyunmin?
Okay, thank you.
Okay. Heejun?
Hello. First of all, thank you very much for the interesting talk. I just would like to hear a comment about the possible role of the Subaru PFS in probing the self-interaction cross-section in the velocity scale around like 10 kilometers per second. I mean, the very low end of the velocity
That's right,
scale.
like 20 kilometers per second or so, yeah.
Right.
Well, so that's what Subaru does is to look at the individual stars in the dwarf galaxy, and it's a spectrograph, so you can measure the radial velocity using the spectrograph, and the accuracy we expect is really of the order of 10 kilometers per second. So you can really map out the velocity profile of the stars in these dwarf systems, and it has 2,400 optical fibers. So in one shot, you can measure the spectra of 2,400 stars at the same time. So you don't need to spend that much time to map up entire dwarf galaxy all the way from the central region to the outskirts in just, for example, 4 observations in the case of Ursa Minor, and even one shot on board is one. That's the ultra dwarf I mentioned earlier.
I see. So do you expect that the error bars in the inferred SIDN cross-section to decrease with perhaps with the PFS?
Yeah, absolutely. And definitely we have much higher statistics. So typically these dwarf observations are done based on only a few tens of samples of stars. And that's why you're still left with rather uncertainties in the actual velocity profile, and especially the density profile, which you need to extract in addition to the velocity profile. But once you have a much bigger statistics, you can even see the kink from this the first slope to the second slope in FW profile. Then you have a much better understanding of what's going on in dwarf systems. So you have a less prone to systematic issues. And also, we can measure the abundance of alpha elements, carbon, oxygen, silicon, using, again, the spectrograph in high resolution mode. So that would tell us about the chemical evolution history, if there had been really enormous baryonic feedback, like required in flattening out the central profile. So we will learn a lot, I hope.
I see. Okay, thank you very much.
All right.
Hi, Toshi, I have a question about dark baryogenesis.
Okay,
so
go ahead.
To explain the dark matter in terms of dark hadrons, I guess you need to have a dark baryogenesis with CP violation and so on. So can you sketch the idea?
So one simple idea is that dark sector is 2 Higgs doublet, and you can have CP violation with this lambda 5, lambda 6 parameters, and you can have the first order phase transition, because we don't know the Higgs mass in the dark sector, so it could still be light enough to allow for the first order phase transition. That's sort of the simplest thing I can imagine.
Okay, I see.
And if you further make the dark sector with 3 generations, then the dark QCD scale evolves from the running of the QCD coupling all the way from gut scale. And maybe it's unified as a string scale. So it becomes sort of not a big coincidence that the QCD scale in the dark sector is sort of similar to the QCD scale in the standard model. And then you can really start seeing why coincidence comes about between the dark matter and our baryons, right?
Right, yeah. How about the dark Axion, for instance? So
I haven't thought about this. Yeah, but you can certainly talk about this. And the one of the models I had with Eric and Univ, together with Caitlin and Robert, is to use the Axion portal between 2 sectors. But typically, the dark Axion, the Axion portal has to be heavy enough to avoid the ineffective problem. So it turns out that the dark Axion has to be pretty heavy, which in turn calls for relatively high QCD scale or low decay constant. So I don't know how interesting that is in the end.
I see. Okay, thanks.
So
right.
The time is up.
No
Sorry,
questions?
can I ask a short question about the effective ranges theory? Because you talked a lot. Because of that, there must be many questions. But let me ask one quick question on the effective ranges theory. That you mentioned that it is unitary and non-perturbative, so it is more appropriate for using it, for instance, for the simulation, the galaxy simulations, or the phenomenology. So do you know? Do you know if people have tried to use it for simulation? I mean the self-interaction.
I know Frank Navarro and Durham is actually interested, so he might do it, but I haven't actually heard that he has finished it. But he was definitely interested in doing that.
Let's see. Okay.
And as you know, if you do a perturbative Born calculation using the Yukawa potential, you typically violate the validity of the Born approximation. So having a unitary description is really crucial, right? So this is already built into the effective range theory. That's why it's kind of nice and easy to use.
So for that, I mean, for low momentum, this is the momentum expansion. So for low momentum, you may capture this range. You have additional parameter which can be determined by the microscopic models. But if you
that's right.
If
so
you
by mapping out this kind of the different systems, yes, in principle you can.
If you go to the higher orders in momentum, you are introducing more parameters, and is it relevant? I mean, for more is it relevant for the more precise determination of the phase shift or self-interaction?
Yeah, I kind of doubt the high order term. I kind of doubt the high order terms are important because the velocity we're talking about is 10 to the minus 3 to 10 to the minus 4 in speed of light, right? So it is really, really non-relativistic. So the momentum expansion should be excellent because of that. And so the truncating at the k-squared order, which is half-spade indeed, must be, completely sufficient for this purpose.
Okay, thank you.
All right, so since we really had a lot of fun, thank you, Hitoshi.
Good. All right,
let's move on to the next talk. Youngjoon Kwon.
Hello, so can I share my screen?
Yes, please.
So can you see the screen?
Yes.
Okay, so let me start. So thank you for this wonderful opportunity of presenting the Bell and Bell 2 physics results, especially on the dark sector searches. So this is a mind map of what Bell 2 can do in terms of the physics. So you can see there are many, many subjects. And today I'm going to focus on only one subject, that is the dark sector. And basically, I'm going to present the results from both Bell and Bell 2 experiments. By the way, officially, Bell and Bell 2 are two different experiments, even though the collaborators are mostly overlap. Okay, so I'm going to show the results that we have published over the past couple of years. So anything older will not be covered. Anything newer or kind of ongoing will not be also covered. So basically what I'm going to talk about is the two Z prime search from Bell and Bell 2. They are two different papers. And action-like particle searches from Bell 2, and baryonic dark matter search from Bell, and dark matter or dark sector related searches from the B-meson decays for either Bell or Bell 2. Okay, so this is a brief review of the Bell and Bell 2 experiments. On the left-hand side, I show you the colorway view of the Bell experiment and Bell detector. And then on the right-hand side, I show you the LiDAR and the Bell 2 detector. So this is a one-page summary of the Bell experiment. We have currently about more than 400 members, but they are mostly also in the Bell 2 experiment, and Berkeley electron-positron collision with 8 GeV electron beam and 3.5 GeV positron beam making upsilon 4s, resulting nearly 1 billion pairs of B-mesons. And on the right-hand side, I show you comparison between BABA and Bell. These are the so-called first-generation B-factory experiments. And BABA achievements include, of course, the CP violation in B-meson decays and CKM precision measurements, rare decays of B-mesons, B-sub-S mesons, and then many spectroscopy of charm dihedrons and quark-gonium spectroscopy and things like that. Okay, then we wanted to do more, so we continue with the upgraded experiment, that is Bell 2 experiment using the Super KKB collider. Basically, Super KKB collider collides electron beam at 7 GeV and positron beam at 4 GeV, and that happens to be nearly the same central mass as in Bell, which used 8 and 3.5. Okay, the main difference is that here on the bottom left corner, I show you the beam profile of old KKB and new Super KKB. You can see that Super KKB is beams are much narrower at the level of 1/20th, and we increase the beam current about a factor of 1.5. That means we can increase the peak instantaneous luminosity nearly a factor of 30. And in the end, we are aiming at attaining the integrated luminosity from Bell 2 at around 50 inverse autobahn, which is about 50 times what we have accumulated in the Bell 1 experiment. And currently, Bell 2 collaboration consists of more than 1,000 collaborators coming from 26 countries and regions and 120 institutions. And this is the current Bell 2 luminosity status. On the left-hand side, I show you the integrated luminosity at the end of last year. Currently, we have resumed the run, so we are adding the luminosity. And by the end of last year, we have accumulated about 270 inverse femtobarn, which is a little less than 1/3 of what we have accumulated in Bell 1. So I think Bell 2 is really contributing seriously to. On the right-hand side, I show you the near-term plan of the Bell 2 operation or Super KKB collider or Super KKB collider operation. Sometime in the early next year, we are planning on long shutdown, in which time we can Bell 2 components. I mean, partially. Okay, then we will with even better performance. Okay, I would just want to comment that Bell 2 has been in operating era with modified working mode in accordance with the anti-pandemic policy, and this page shows you a summary of what we have done. Okay, so let me move to the dark sector search results. Okay, so for both Bell and Bell 2, basically we are operating on the same central mass energy. Basically, what we search are nearly identical. So we search for dark matter or dark sector particle with the mass of around a few GeV, because our central mass energy is about 10 GeV. And if we can find the signature of the vector polar particle like dark photon, or maybe some new type of vector gauge boson, the L mu minus L tau Z prime, then they may explain, for example, G-2 muon. And the typical processes that we are looking for are the E plus E minus producing some standard model particle. Sometimes it can be a single photon, as Hitoshi just mentioned, plus the dark sector mediator. Or we can look for the processes like B-meson decays to a bunch of standard model particles and some mediator. Okay, so let me start from the leptophilic Z prime search. If this leptophilic Z prime is from the L mu minus L tau model, then it can hopefully explain the G-2 muon anomaly. And it could also be a channel for sterile neutrinos as a dark matter candidate. And today I'm going to show you two results. One is the search for Z prime to mu mu from Bell, and another one is search for Z prime to invisible final states from Bell 2. Okay, so let me start from the Bell 2 physics results. This particular PRL paper is the very first physics paper that we have published from Bell 2. In this paper, we search for invisibly decaying Z prime boson in the decay process E plus E minus producing a muon pair, which when one of the muon radiates the Z prime, and Z prime then decays to invisible final states. Since this Z prime is, we are assuming that since this Z prime is gauged in L mu minus L tau, they cannot decay to E plus E minus pair. The Z prime mass is below the muon threshold, then it is only sensitive to the neutrinos or some light dark matter particle which is invisible. Okay, so in order to run, we have studied the generic Bell 2 Monte Carlo and data events, and we found out that particular analysis, the most serious background is coming from E plus E minus to tau, where E2 muons and a bunch of neutrinos. So in order to suppress the tau background, we have devised a special PT dependent cuts. And it is shown in the left-hand side plot where the red is for the signal and blue is for the tau background. And basically they are related to the PT of recoil Z prime with respect to either lepton of higher momentum or lepton of lower momentum. So with some diagonal cuts, we can basically make it very clean for the signal candidate events. So this cut is mainly to suppress the EE to tau background. So at the end of the day, we have opened the data box and found out that on the right-hand side, sorry, the signal yield of E plus E minus 2 mu mu and some missing energy momentum is basically very well consistent with what we expect from Monte Carlo's generic background events. So the black dotted points with arrow bar are the BEL2 data from 276 inverse picoband, which is basically 1,000th of what we have in BEL2. And all these colored part is the accumulated Monte Carlo simulation. In addition, we have also searched for the E plus E minus decaying to E mu pair. Basically, that is related to the lepton flavor violating Z prime. And in this case, also, our result, the data points are very much consistent with what we expect from the background. So we conclude we don't have any signal. So we set upper limits on the G prime, which is the coupling strength of this Z prime to the muons. Okay, so this blue curve is our limit. And just for the fun of it, this red band is what we expect from G-2 muon anomaly if this is all to be explained by this extra Z prime. So we are a couple orders still bigger, but I just want to focus it again that we have 1,000th of the data sample that we already have in hand. So with much more data sample, we hope we can do near or even we can exclude all this red band if we don't have any. Just for the fun of it, on the right-hand side, I show you the BEL2 simulation. If we analyze 50 inverse femtobarn, remember we already have 270 inverse femtobarns and clearly kind of exclude much of the region for the G-2 band. Okay, let me move to the analysis for the leptophilic Z prime search, which was submitted to PRD in last fall and still in the reviewing process. We look for Z prime mu mu in E plus E minus 2 mu mu Z prime. And I show you some brief summary of what we do for the event selections. Basically, we look at the sum of electromagnetic calorimeter cluster energies not matched to any charge tracks. And that should be consistent with 0. And we apply J psi beta because J psi to mu mu is a huge peak that we cannot, ignore. Okay. Then we scan for any resonance in the mu mu mass, but we scan with reduced mass MR, which is defined as M mu mu squared minus the threshold mass squared. So MR is the fit variable for signal extraction. So on the right-hand side, I show you the MR distribution. Black is Monte Carlo simulation, red is data. And what we are doing is we look for any resonant-like signature in this red distribution. And the irreducible background is the ordinary standard model process producing EE to mu 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 mu, and Z prime to mu, the J psi to mu mu is one of the irreducible background. Okay, so on the right-hand side, the red data point is from the integrated Bell luminosity of about 679 inverse femtobarn. Okay, and basically we don't see any resonant structure, and The one that shows the highest local significance of about 3.2 sigma is for the MR mass around 141 MeV. That corresponds to the Z prime mass of about 254 MeV. But after applying the Look-Elsewhere effect, the significance goes down to 2.2 sigma. So that's nothing to be excited about. So we simply set upper limits on the G prime, the coupling strength, and the result is shown as either red or on the right-hand side plot. Red is for the bone cross-section, and blue is for the visible part. And around 100 MeV to about 5 GeV, we kind of exclude band, and our result is comparable to what Baba has obtained. Okay, the search for axion-like particle at Bell2, which was published a couple of years ago. So we search for axion-like particle process E plus E minus going to a photon and the axion-like particle, where axion-like particle A decays to a pair of photons that results in 3 photon final states, or the axion-like particle decays to invisible final state. In that case, our final state will be a single photon plus missing energy momentum. So we look at the mass of the axion-like particle distribution, and for the photon threshold, we apply the mass of axion-like particle dependent cuts. So when we look for the MA less than 4 GeV, we require that photon threshold should be bigger than 1 GeV. But when we look for the MA bigger than 4 GeV, then we loosen it down a little bit to about 650 MeV. And if you look at the right-hand side plot, this shows you the mass square resolution for the axion-like particle mass. But in this case, there are 2 bands. One, the orange band is when you look for the diphoton final state, and the blue band is when we look for the recoil mass for a primary photon. So at around 6.5 GeV, exactly it is about 6.8 GeV. If it is below 6.8 GeV criteria, then diphoton system has much better resolution. While for the higher mass region, the recoil mass measurement is much better resolution. So we decide that we will look for the diphoton mass square that is 3 photon final states for the axion-like particle mass between 200 MeV to 6.8 GeV, 6.85 GeV. On the other hand, we look for the recoil mass square when we look for the axion-like particle with mass bigger than 6.85 GeV. So in the bottom left corner, the left side plot is the recoil mass distribution, and the right-hand side plot is the diphoton mass square distribution. So in any case, we don't see any resonance structure. And in this page, you see the significance plots. Basically, everything is below 3 sigma. So there is 3 sigma. So there is not any hint of any excess. The maximum local significance happens at 177 MeV. So that's a little less than 3 sigma. So we set upper limits cross-section of E plus E minus going to photon and axion-like particle, and everywhere the cross-section is around or below 1 picobarn range. Okay, this is upper limit. So from this upper limit on the cross-section, we set the limits on the coupling of axion-like particle photons, and you can see that between about 200 MeV to about 3, 4, maybe 5 GeV range, Bell2 is the most stringent among all the players in the world, at least so far. Okay, let me move to the dark sector search from B-meson decays. And so the first one is what we have published last year, that is search for dark photon process in B0 decays. Basically, the process that we are concerned about is this B meson decays to a pair of dark photons, A prime, that is produced through the mixing of standard model Higgs to dark Higgs, and each dark photon decays either to L plus L minus or pi plus pi minus. And basically we scan the range between the MA prime between 20 MeV to 2.6 GeV, that's about half of the B meson mass, with full data sample at epsilon 4s. And this is very clean measurement. So as you can see in the picture below, we have only a couple of events except for the pi final state everywhere in this A prime mass region. So we set upper limit on the branching fraction that is shown on the left-hand side here. And on the right-hand side, we convert our branching fraction upper limit into the parameter lambda, which is describing the dark Higgs and standard model Higgs coupling. So basically we set upper limits on the H prime coupling strength. Various different colors on the right-hand side plot corresponds to various different assumption of the dark Higgs particle mass. And for this case, all these kinematical cross-sections and the conversion relations are from the two papers by Patel, Pospelov, and Ritz in PRD about a decade ago. Okay, another results that I want to show you today of dark sector search from B meson is the very new paper that we have submitted last year, that is searching for baryonic dark matter, which we DS. So in this case, we look for the B meson decays to lambda, which is the ordinary lambda plus the missing energy momentum, because we are concerned about this baryonic dark matter. I mean, either does not decay or decays to invisible states in our case. This measurement is inspired a recent paper by Elo, Escudero, and Nelson, which was published in 2019, and that under some models that explains the so-called beam mesogenesis, that is the explaining baryogenesis and dark matter with B meson decays. They predict that this decay branching fraction should be bigger than 10 to the minus 4 under some assumptions of models. So if we can have significance or sensitivity either around 10 to the minus 4 or better, then you can make very interesting fact on this paper. So the existing limit is this branching fraction should be less than a couple of 10 to the minus 1 was very old, Aleph around 2001. And also we just want the baryonic dark matter under the mass 3.5 GeV is indirectly constrained by CMS and Atlas from V-scale color triplet colors. And in the bottom of this slide, I show you the decay diagram of B meson to lambda and baryonic dark matter psi ds. The better strategy is that we'll use hadronic B tagging for lambda plus nothing in the signal B meson decays, as we briefly show in the picture on the bottom of the page. And we use the extra energy in the electromagnetic calorimeter for background suppression. Basically, we require that E sub ECL should be less than about 0.5 GeV, depending on the psi ds mass. On the right-hand side plot, I show you this E sub ECL distribution for the data, which is black points and various background. And the dashed signal is assuming the psi ds mass is about 2.5 GeV with the branching fraction 8 times 10 to the minus 5. Okay, so this is the search result. On the left-hand side plot, we didn't see anything basically. So we set upper limits on the branching fraction of B0 to lambda psi ds. The upper limit is around a couple times 10 to the minus 5 in the mass range between 1.0 to about 3.5 of psi ds. Since we don't see any signal, we set the upper limits on the branching fraction. Okay, and on the right-hand side plot, we convert this. I mean, we compare this upper limit of the branching fraction. So these black points are basically the same black points between left and right, and the overlaid orange and blue colored shade is what is predicted by this theory paper, Alonso Alvarez, Elo Escudero, PRD 2021. So basically, we exclude this blue shade region, that is the so-called type 2 and type 3 hypothesis on this theory paper, up to the psi ds mass around, I mean, down to psi ds mass around 3.0 GeV. So anywhere 3.5, 3.0 GeV and up, this type 2, type 3 models are excluded. But this type 1 model, which is orange band, is still alive. Okay, the final topic that I'm going to show you today is search for B2K nu at Bell, but since my time is almost, so in the standard model, B2K nu is calculated to be around 5 times 10 to the minus 6 clean, because neutrinos do not interact much. So there is not much uncertainty, and this is sensitive beyond the standard model, for example, lepton model or actions or dark matter particles. And existing measurements and upper limit mass 5 range. And for the Bell 2 analysis, we look for highest transverse momentum with at least one vortex hit track as a signal K1. And then we look for all other tracks and clusters as rest of the event. And then we apply the BDT for signal discrimination. With this, we use event shape and the rest of event dynamics and signal beam-meson kinematics and vortexing information. So BDT information is shown in, and one of the variable for the BDT, the so-called sphericity, is shown as a plot number 3 on the right-hand side here. Then we apply this BDT in 2 stages. In the first stage, we suppress the continuum background, and then in the second stage, we suppress the rest of the background. Then our signal region is defined in 2 dimensions. One is the second BDT output variable, and the second one is the transverse momentum of the K1. Okay, then we check BDT output with B2J psi K control sample for both the signal and background, and you have to read the paper for any details. And then also we check the data Monte Carlo agreement using off-resonance data. Finally, we apply simultaneous maximum likelihood fit to on and off-resonance data and obtain the signal yield. And we didn't see any signal, so we set the upper limit of branching fraction to B2K nu at around less than 4.1 times 10 to the minus 5. So on the right-hand side, this is the current summary of what we have in B2K nu. The top one is what we just present from Bell 2, and the bottom 3 are the existing measurements and the limits from the Bell and Baba. So even though our measurement has very large error, remember, if you look at the data size, Bell has used 700 inverse femtobarn, Baba has used 429 inverse femtobarn. Our data sample is about only 1/10 of the data sample. So considering that, our new measurement is very kind of sensitive to the, I mean, very nicely sensitive to this analysis. So we think this method is very promising. Okay, so as a closing remark, I just wanted to point out that E plus E minus B factories show that they can also contribute to dark sector studies. So with the Bell 2, the exploration shall continue. Thank you very much.
All right, thank you. So questions?
Hello?
this scheme.
Yes, please.
About B2K no. You have something like 10 to minus 5 branching fraction. And you are going to have about more than 10 to 8 fully reconstructed B. So that means about 1,000 events. Why still you cannot just measure such not many events?
Let me show you the screen again. Okay, so as you can see, our belt 2 data contains 63 mass femtobarn. We currently have 270 mass femtobarn, 17 mass femtobarn, and we are aiming at having 15 mass autobarn. So 15 mass autobarn and 63 mass femtobarn, that's 800. So eventually we will have 800 times more data, but not now.
I see.
Yeah.
Okay, Hitoshi? No.
Yeah, I have a question. So do you have already a monophoton trigger implemented?
That is implemented. Analysis are going on, but we don't have any public results to show. Sorry.
Oh, okay. But the trigger exists.
Because of the limited time, I didn't show any ongoing efforts. Yeah, very sorry about that.
And we hear the background situation is pretty bad compared to expectations. What is the current status?
The current status is that it is not as clean as the old Bell experiment. That's what I can say.
I see.
But we are working hard.
Okay.
So, Song-Chan?
Yes, Professor Kwon, do you have some program to explore long-lived particle searches? You didn't show anything about that.
There is an activity
I see.
about the long-lived particle search. Basically, in the Bell 2, dark sector physics group is very active compared to in old Bell 1. In the Bell 1, dark sector group is more like a hobby. So a few people working on some hobby project, but in Bell 2, it is very hot project.
I see.
So you can expect, more.
Okay, thank you.
Right. So
what about Gazelle? Is that officially dead?
Excuse me?
Gazelle. Gazelle project, the forward detector.
I'm not very good about that, so I'm very sorry. Maybe I can check with my friends. Yeah.
Okay.
All right. So if there are no more questions, let's close the session. Thank you, Youngjoon Kwon. So
thank you very much.
So we resume after lunch.
Yes, we will resume at 1:40 p.m.
1:40 p.m. Okay, good.
Okay.
See you soon.
Okay, thank you.
Bye.
Bye. Thank you.